Hi, this is Dr. Staley, and today we're going to be doing Chapter 7, Lecture 1. We're going to be talking about quantum theory and atomic structure. Now, quantum mechanics, quantum as in small discrete things, mechanics as in work or labor, like manual labor, mechanicos. So we can think of quantum mechanics as just the way that small discrete things work. Now, the quanta in quantum mechanics refers to the small packets of energy that need to be exchanged between different systems as the internal energy of those systems goes up or down. And the easiest quanta to study, far and away, is light. Now, when we're studying light, we're studying optics, which comes from a Greek word meaning sight or to see, but this just means the study of light. And what you might have guessed from the fact that we take it from the ancient Greek is that optics has been around for a very long time. But specifically the observations that have been studied over and over again are the observations of the existence of color, reflection, refraction, and diffraction. The work that's usually quoted as being the seminal work on optics, at least if you live in an English-speaking country, is Isaac Newton's optics. Which so that was published in 1704. Doesn't actually matter the exact date. But that dealt with color and refraction. Now, the reason that Newton got interested in optics was because he saw a problem with telescopes in his time. See, the only telescopes in his time were the kind that had lenses that were, made of glass, and the light would come in and then it would focus, the light. Now, what Newton noticed was that if you have a circular spot of light and it goes through the glass, then its angle will change, but importantly, when it comes out, it'll be elliptical instead of circular. And what he noticed is that, if it hits at a certain angle, then that ellipse, that ellipse will have different colors in different places. And so that led to him designing a telescope based around reflection instead of based around focusing on lenses. However, when he did similar experiments with glass prisms, where he had light coming in, hitting the prism on one side, he would get out on the other side a variety of different colors that were separated from each other. A spectrum of color. And if he started with light that was white over here in the beginning, he would get all of the colors in existence. This observation was important when dealing with color, because one of the ideas that was around beforehand was that color was just something that is inherent to an object, and as long as you have light hitting it, you will be able to see whatever color that object is. But this led to the observation that, put it in a different color, that light is already colored. And that colored objects just reflect some of the colored light. But it also led to another observation, which is that when light bends inside an object, it bends according to which color it has. So that second observation of refraction is that refraction is due to some colors of light being bent, by which we mean that the path that the light takes is bent, more than others when going from one material to another. Now, Newton proposed that the difference in the materials had to be a difference in density. That's not exactly the case. We call it a difference in refractive index. It is related to density, but it's not the same thing. Now, Newton's proposals in optics had a couple of assumptions. The first of those assumptions was that light is made of particles. The second assumption was that light has different speeds in different materials. And thirdly, unfortunately, in order to make refraction make sense, he had to use the equations associated with waves in order to explain why different colors of light were refracted at different angles. Now, this first assumption up here was probably just a guess. But as we will see, this assumption turned out to be right. Actually, all of them turned out to be right, but it's kind of surprising that the one that was a guess also turned out to be right. Now, how does assuming that light moves in waves, how does that explain refraction? How does this actually, so reflection, so how does this actually explain refraction if we assume that light is a wave? Well, first, let's look at what a wave is. A wave, like a sound wave, for example, you could make, so for a sound wave, you could look at the density of air, and then over here, distance. So what a sound wave is different densities of air moving forward. If you have, or coming towards you. And so when those different densities of air hit your eardrum, they, the high densities push it in, the low densities pull it out, and so so your eardrum goes back and forth like that and vibrates. So if you make a graph of the density of air versus the distance, what you end up with is something like this. This is what we call a sinusoidal wave. it has a general equation of y equals a factor there, sine nu x, Greek letter nu, where a is the amplitude, how high it is, amplitude, you got the high pressure here, the low pressure there, and we've got another and we got another property which we call the wavelength. So if you go from here to here, for example, this is the wavelength. The thing about a standing wave is that it's just the same thing repeating over and over and over again. So if you took this segment and just copied it and pasted it onto here, you'd get this segment. If you did the same thing there, you'd get this segment. If you did the same thing there, you'd get that segment. So we can think of the wavelength as just, well, the length of the wave. Yes, I know that's pretty self-explanatory. But the wavelength is related to the frequency. So with a standing wave, it's not doing anything. But with a wave that moves, there is also the frequency, which is how many wavelengths pass a point in a given time. Wavelength is usually given the symbol lambda, that's a Greek letter, and frequency is usually given the symbol of the Greek letter nu, which looks very much like a V but is not actually a V. And so if we have the frequency, that's frequency equals number of wavelengths over time. And we multiply this by the wavelength, then what we end up with is the speed of the wave. Now, I gave an example here of sound waves. Well, I'll explain how this relates to the speed. Well, I gave an example here of sound waves, but if you look at this as light waves, then the wavelength times the frequency is the speed of light in a given medium. Now, here's how this affects the here's how this explains refraction. If you have a barrier here between two materials, material A and material B, let's say air and glass as an example, and you've got light coming in with a certain wavelength and hitting it, well, what changes in the wave is the wavelength. The frequency of the wave does not change. And that causes the speed of the light to change, but it also causes the angle to change, because the angle at which the light hits the barrier between determines the angle that it comes off at on the other side. And so if you have a wavelength that is medium, that is one wavelength, and then you have a different wavelength that is a lot longer, well then, when you come off on the other side, you're less likely to hit the other side at a very steep angle, and therefore the light is going to have a much more shallow angle for light of a long wave. The angle of refraction is going to be much shallower for light that has a long wavelength as opposed to light that has a shorter wavelength, or light that has a very short wavelength. Yeah, I accidentally be more like. And so this would be why light refracts at different angles depending on the color of the light. And this is one of the reasons why later physicists that studied light just went ahead and assumed that light worked exactly the same as sound, where they threw out the idea that light was made of particles and just focused on the wave nature of light, because that explained everything they needed it to explain. One of the things that this went on to explain very easily was the what we called the Two-Slit Experiment. So if you take a box that has a hole in one side, and you hit it with a bunch of particles, then what ends up happening is that most of the particles just hit the side of the box, and the ones that hit the hole go straight through, and you end up with the particles hitting the back. If you hit it with a set of waves, so, just drawing the crests of the waves, they'll end up looking like this, because, they go up and down and up and down and up and down and up and down and up and down, like that. So I'm just concerned with the crests right here. Then what will happen is that the waves that go straight down the middle here through the hole will go straight down the middle. But on the edges, the waves will start going around the edges. And so the crests of the waves here will start to be like this. And you'll end up with the crests hitting this part near the end, just like the particles do. So far, so good, right? Well, suppose, so this is the one-slit experiment. Well, suppose you had something, a phenomenon, and you wanted to know if it's caused by particles or waves. Well, what if you did the same thing, but with two slits? Well, now, with the box that has two slits, there we go, two openings, for the example involving particles, the situation is just exactly the same. Particles come in, a bunch hit the sides, and then a bunch go through. And instead of having one spot, you have two spots, each of which are directly opposite the place where the particles came in. Are directly opposite the slits in the box. But for waves, the situation... Yeah, you can tell I am not an artist. For waves, though, the situation is a bit different. So, once again, we've got our waves here and focusing on drawing the crests. So that these lines, they just represent the crests of the waves. Because the waves diffract, this is diffraction. The phenomenon where it bends around the corners. Because the waves diffract around the corners, and there are now two slits, you now have the situation where this slit will go like this, and the waves from this slit will do something similar. So that what you end up with bright spots, you end up with bright spots that are not directly opposite the slits, but rather you end up with a series of bright spots that happen where the wave crests overlap. Because just like with sound waves, all your ear is detecting is whether or not it's being pushed or pulled. So if you have waves that overlap with each other very well, then that gives you a single bigger wave. Whereas if you have waves that overlap with each other, if you have waves that are the antithesis of each other, then they end up nullifying each other and you get nothing. These things are called interference. And this one is constructive interference. This one is destructive interference. So over here, where you end up actually seeing the spots on the end from the energy hitting the wall is you end up seeing that wherever the waves interfere constructively. And you end up seeing dark spots where they interfere destructively. And when this experiment is performed with light, When this experiment is performed with light, the result is that we get an interference pattern instead of just a bunch of particles hitting the back. So the color of light indicates that that color is a property of the light. Reflection we haven't really touched on, and we're not going to. Refraction is most easily explained by light having waves, and diffraction, this, is also most easily explained by light being waves. So the analysis, the idea that light is a bunch of waves led to a very obvious question for everyone. With sound, like, you hear something because those are vibrations, those are pressure differences that are happening in the air. So sound waves that hit your ear are waves that are where what is waving is the air. So here's a question. If light is purely waves, what is waving? Because if light is waves, then it's just a phenomenon unto itself. I mean, the example that I used with sound was sound hitting your ear when, was sound hitting your ear from vibrations in the air. But if you go underwater, you can still hear things. Those are vibrations in the water. Sound is just the substance itself vibrating. Vibrations can, sound vibrations can go through solid objects also. So the sound is not really a substance. It's a phenomenon that another substance has. So in case of light, if it's waves, what in the world is it that's waving? Well, that led to the proposal that there is an ether that permeates the universe, and light is its vibrations. And so, let's say that you live on a rock, and that rock is going around the sun at a rate of 67,000 miles per hour. Well, in that case, when the piece of this rock that you are on is on this side, because the rock happens to be spinning at the same time, you are going an additional 1,020 miles per hour. And when the part of the rock that you're on is on this side, because again, it's spinning, well, since it's spinning, you're going another 1,020 miles per hour this way. So what that would mean is that the speed of light is as much as 2,040 miles per hour faster when you're on this side of the Earth, when the part of the Earth that you're on is on this part of its spin, versus when it's on this part of its spin. And that's the reason why the speed of light changes depending on the hour of the day. Except that doesn't happen. the speed of light does not change with the time of day. And so what that means is that this has to be wrong. Where's the damn thing? Yeah. And so what that means is that this has to be wrong. And that was a problem in optics for a long time. Now, but that's not the only problem in optics for a long time. The other problem is blackbody radiation. So blackbody radiation is actually pretty simple. Blackbody radiation is just things start to glow when they heat up even if they start out black. Now, if you look at this as the intensity, at the amplitude of the radiation coming off of it, and you compare it to the wavelength of the radiation coming off a black body, then what you see is that at any given temperature, the radiation follows a pattern that looks more or less like this. And that as temperature increases, the curve just goes up. And that's the reason why when you preheat your oven to 350 degrees so you can make some pizza, and then you go to open the oven to put the pizza in, you immediately die because of the low wavelength, high energy gamma rays coming out of your oven. Except that also doesn't happen. This is what would happen if light was purely waves, because the low wavelength light is a more efficient way of getting rid of energy. But what happens instead, so what happens instead is that with blackbody radiation, got the amplitude that way, the wavelength that way. What happens instead is that you get a distribution that looks more like this. So that it, sorry, let me redraw that. So that as the temperature increases, the blackbody radiation both grows in the amount given off and also shifts to the lower, and also the peak of it shifts to the lower wavelengths. So that at extremely high temperatures you should get something like this, and indeed with astrophysics observations you do. But the exact peak, but where the exact peak is determined by the temperature. And this is also the reason why when you heat up a piece of metal really, really hot, it goes from nothing to red to blue to eventually white when all of the light is saturating everything. And so this is what actually happens, but this is what should happen if light was purely made of waves. Now, Max Planck, in I think right around 1900, Max Planck proposed that light is made of particles our quanta and when he made that assumption, okay, that light is made of particles, that quanta, and that the reason why hot objects start giving off light of lower wavelengths, the reason why they start giving off light of lower wavelengths is because you have to have a certain minimum amount of energy in one specific atom in order to make it give off light that has one of the lower wavelengths. So what do we mean by the energy in light? Well, remember how we said before that if you multiply the wavelength by the frequency, lambda by nu, you get a speed? Well, in the case of light, you get a certain speed that is dependent upon the material that the light happens to be going through, c. So the value of c is 3.00 times 10 to the 8 meters per second in a vacuum, which is essentially its maximum speed. And so, because of this, we can tell that, and so because this is a constant, what that means is that while these two are variables, they vary relative to each other. So that if you want to just know the wavelength of something, well, the wavelength is based on the speed of light and the frequency. If you want to know just the frequency of light, well, that's based on the speed of light and the wavelength. Now, the the way that Planck ended up getting graphs that looked like this, based upon the different temperatures, is that he proposed that the energy in a sample of light is equal to the number of photons. Let me write this in a different color. He proposed that the energy in a sample of light is equal to the number of photons times the frequency of the photons times a constant. So this is G of sample of light. This is the number of photons. This is the frequency. And then this one right here, H, is Planck's constant. Which is equal to 6.626? Yep. 626 times 10 to the negative 34 joules per second. And Planck's constant is a conversion factor. Yeah, so I keep coming back to it. Gen Chem, there's just metric tons of unit conversions. So the energy, you got a conversion factor to go from frequency to energy, and number of photons. And that's how he was able to get the distribution of wavelengths of light in blackbody radiation. Of course, why is light quantized? He didn't know. Why is light quantized? He didn't know. He didn't have any idea. But there was another clue to light being quantized is what we call the photoelectric effect. Now, if you have, let's see. So let's start out with blackbody radiation. Now we've got the photoelectric effect. What the photoelectric effect is that when you have a metal of some kind and you've got H nu and you have light that shines on it, you can actually cause electrons to be ejected from the metal, to leave the metal. And this shouldn't really be that. It should be a lot more straight like that. Yeah, you end up having electrons leave the metal. Now, if you have something where you got, let's say, a metal rod and then a metal sheet that's right next to it, and you happen to, suck all the air out of out of it and you connect them to each other, what ends up happening here is that with light coming in, the light will end up hitting both of these, but because the sheet has larger surface area, the sheet ends up getting more light hitting it, and so it ends up getting electrons being ejected from it and ending up on the rod, which causes the electrons to then go through the wire, and you can detect that as current. Actually, a similar situation, but with semiconductors, is currently used for an awful lot of solar cell technology. Anyway, so this is the photoelectric effect. And some interesting observations about the photoelectric effect is that the amplitude of light didn't determine the number of electrons that are ejected from the metal. So if you were to assume that light was just purely waves, then the amplitude should be the only thing that matters, because a larger wave would throw an electron off no matter what its wavelength was. But that was not the case. Also, there is a threshold frequency for ejecting electrons, where even if you have a very low intensity and therefore very low amplitude of light, but that light happens to be above a certain frequency or below a certain wavelength, then you get current. Whereas even a high amplitude or high intensity of light at a longer wavelength and lower frequency, you don't get any current. And finally, the amount of electrical current was proportional to the number of photons, number of particles of light above the threshold. Above the threshold frequency. So that added more evidence to the idea that light was indeed particles in addition to being waves. And then finally, we've got another observation that came from light being, well, it came from the fact that when you look at the solar spectrum, it doesn't actually contain all of the colors. So you remember how with, Newton, we said, oh, that, that he had his prism and, he shined light through it, and what he got out on the other side was this, was the spectrum, right? And if you started with white light, he ended up with the whole spectrum. Well, it turns out that if you do this with sunlight, you don't get the whole spectrum. You get, I need to double check the exact numbers, at 3 lines or 4 or 5. Oh, that one's the one that's not actually in there. So that the solar spectrum going from red on one end to, I think, violet is what we call the color on that other end. It actually has some dark spots in it. 1 there, and then 3 over here. Now, that seems kind of odd, and for a long time, people were trying to reproduce that. The way it actually got reproduced, though, was going at it the other way, where instead of having a solar spectrum, we had an emission spectrum from hydrogen atoms. And that emission spectrum had bright spots where the sun had dark spots, and it was dark everywhere else. And so this was considered to be the spectrum of hydrogen atoms, where if hydrogen releases light in these specific wavelengths, when it's heated up hot enough, then perhaps it absorbs light of those wavelengths also, so that the lines in the solar spectrum are due to light being absorbed by hydrogen atoms. Oh, the way they got these hydrogen atoms, by the way, is they filled a tube full of H2, hydrogen gas, and they ran a current through it. If you put enough energy into it, you can break the bonds. We talked about that in bonding, and we talked about that in enthalpy in the last chapter. So they ended up getting these solar lines, and they ended up saying, now, what in the world is going on here? Well, one of the observations made about this was made by a Swedish physicist named, his first name Johannes? I really should type out a whole thing. Yep, Johannes. Johannes Rydberg. And he came up with, and what he figured out was that there's a relationship between the wavelengths of these lines, where if you have 1 divided by the wavelength, then you can relate the lines to each other by a constant called that he named after himself, because of course he did, the Rydberg constant. And yes, this is another R. Yes, there is an R that is a gas constant. No, they don't have anything to do with each other. Anyway, the Rydberg constant, and multiplied by 1 divided by 2 different n squares. Rydberg had no idea why this relationship existed. Where if you took the where any of these wavelengths, you could put the wavelength in here and you could figure out what this N1 and N2 were, and then that was just like that. So the Rydberg constant, by the by, is 1.097 times 10 to the 7th 1 divided by meters. So times 10 to the 7th reciprocal meters. And obviously, because that's in meters, this has to also be in meters. If you measure this in nanometers, then you have to change that too. And then you have to convert the whole thing too. So he came up with this, but he didn't know what that relationship could be. And that actually led Niels Bohr to propose, to take the nuclear model of the atom and combine that with the Rydberg equation and make a very interesting proposal. So, yeah. The clear model of the atom. What Bohr proposed is kind of, well, I'd love to leave this whole thing up here, but unfortunately I can't. I need more board space. So, from the nuclear model of the atom, we have the nucleus in the center, which in the case of hydrogen is just 1 proton. And then we've got the electrons going around it. Now, Bohr proposed, well, what if the electrons have only very specific orbitals that they can be in? And that these orbitals correspond to the different possible values of these two n's. So one of the things that, I forgot to put in here before, is that n1 and n2 are whole numbers And N2 is, it has to be bigger than N1. Because since the ends are in the denominator, the larger the n, the smaller this fraction is going to be. So, this has to be a positive number here, so therefore this fraction has to be smaller so that this remains positive. That means this has to be a bigger number. Anyway, and Bohr proposed that when an electron goes from one energy level to another, it releases light. If it goes down an energy level, and when it goes up an energy level, the only way that it can do that is by absorbing light. So Bohr's assumptions were these. Let me get some more space here. So Bohr's assumptions were these. First, that electrons can only orbit nuclei at specific distances. Sorry, for a minute I lost track of the microphone. That electrons can only orbit nuclei at specific distances. Two, that atoms don't release or absorb photons when an electron is in its normal orbital. I said orbital. Orbitals come later. When an electron is in one of its normal orbits. Three, that atoms do absorb or release photons when electrons change orbits. Now, remember what we said in the last chapter about internal energy, where the internal energy of a system is the total of the system's kinetic energy and the system's potential energy. Because electrons and protons are oppositely charged, they are attracted to each other, so that there is potential energy in an electron in a higher energy level, in a higher one of these orbits, that it can go down to a lower orbit to get closer to the proton. But in order for the electron to maintain its higher energy orbit, it has to have a lot of kinetic energy. And so, photons being absorbed or photons being released, this is a change in internal energy, where the change in internal energy when a photon is absorbed is greater than 0, and the change in internal energy for the atom when a photon is released is less than 0, because it's losing energy when a photon is released, because that energy is now in the photon. It's gaining energy when a photon is absorbed, because the energy from the photon is now in it. And that brings us back to what we said before about how the energy in a photon, this is Max Planck, is equal to Planck's constant times the frequency. Now, because the frequency is related to the wavelength through the speed of light, you can rewrite this as hc over lambda. And so you can apply Bohr's assumptions to the Rydberg equation to get the energies at which light is absorbed or emitted by hydrogen atoms. You can apply that by just, you've got lambda on the bottom of a fraction here. You've got lambda on the bottom of a fraction here. So if you multiply the whole thing by Planck's constant and c, then you can turn this into the energy change of accepting or releasing a photon. So that the change in energy of a hydrogen atom when accepting or releasing a photon is hc over lambda, where lambda is the wavelength of the photon. And that gives us hc Rydberg constant times the quantity 1 over n 2 minus n is 1 over n 2 squared. Now we just have to make one more change, and that is that because this is supposed to be the wavelength of light that is released, this is actually going to be a negative number here. And so it's going to be the electron going from a higher orbit to a lower orbit, so that the higher number here is the initial orbit, the one that it starts in, and the lower number here is the orbit that it ends up in. And because this refers to the photon, but this refers to the atom, it's actually the opposite. Remember how I said how when we were talking about enthalpy and we started with internal energy, and I said, well, if you look at it from the perspective of the system, it's losing energy here, and so therefore the internal energy goes down. This is from the perspective of the photon that's being released. So looking at it from the perspective of the system, this needs to be a negative. So now, don't really need the Rydberg equation here. And I can take this whole thing and rewrite it. So we've got change in energy equals negative C, Planck's constant, Rydberg constant, 1 over, and this is the hydrogen atom, the number of the orbital that the electron is in the end, final, minus 1 over the number that it starts in, initial, that's squared. There. Now, when we multiply this whole thing out, we end up coming out to delta E for hydrogen equals negative 2.18 times 10 to the negative 18 joules times 1 over n squared final minus 1 over n squared initial. And for some reason, Bohr did not choose to just give that a different constant name. He just left it like that. But one of the things to recognize here is that change in internal energy is not just the, it does not just have to do with photons. Again, remember back to the last chapter. The change in internal energy is the final energy minus the initial energy. So we can get from here back to the energy, the total internal energy of any of these individual states, because delta E H equals E final minus E initial. And so by the commutative property of multiplication, this multiplied by that whole thing is the same thing as this multiplied by that minus this multiplied by that. So that part gives us the final energy, that part gives us the initial energy. We can simplify that whole thing by saying that the energy of a given state of the hydrogen atom is equal to negative 2.18 times 10 to the negative 18 joules times 1 over the quantum number that tells us which orbital the electron was in, squared. Now, Bohr's model, including this, turned out to be very accurate, but the reason that it ended up being even more important than that is because he was able to make this model accurate for atoms that were not just hydrogen. And the reason for that is that this one so this number right here, and also this number, and also this number, and also this number, and also that number. That number is a 1, because hydrogen only has one proton. See, the potential energy between the nucleus and the electron is because they have different charges. But the amount of the difference, also affects the potential energy. So, if we take this out, just to give myself some more space, I hate that this is so small. So we can actually rewrite this as the internal energy of an atom is equal to negative 2.18 times 10 to the 18 to the negative 18, right? Yeah, negative 18 joules times z squared over n squared, where z is the number of protons in the nucleus. So the internal energy of an atom is equal to this constant times the number of protons in the nucleus squared divided by the quantum number of the orbit that the electron is in squared. We're going to go into why the electrons only have certain specific orbits in the next lecture, and also why they're spaced far enough apart that this holds true. But I want to point out that, but before I do that, I want to point out that this equation, brought back to the delta H, where you figure out the internal energy for one orbit, then the next orbit, then the next orbit. This equation actually holds true for every atom or ion that only has one electron in it. We call it the one electron atom model. So hydrogen atoms only have one electron. Helium, if you take helium and you ionize it so that it's He+, that only has one electron. You can also do something similar to lithium and beryllium. I don't believe that anyone's ever done something similar to anything beyond beryllium, but you can make all, I don't believe anyone's ever studied that way with something higher than beryllium, but with all of those atoms, they all follow this very simple equation. Now, the reason for that is once you start adding on more electrons, the electrons themselves interact with each other, and that throws around everything. So that makes things a lot more complicated. Anyway, this concludes this lecture. We've just finished section 7.2, and we're going to go on to 7.3 next time.